Hello, nice to see you. Okay, so far, not many people have joined. Let's maybe wait a couple of minutes, then we will start discussing kinetic theory of ideal gas, or in other words, molecular model of ideal gas. That's kind of very important link between macro and microscopical properties of gases. Okay. Hello, everyone. Nice to see you guys. So this week we start with a discussion of kinetic theory of gases. And we will try to find relationships between macroscopic state parameters, which are temperature, pressure, and volume. But volume is defined by the container. So parameters like pressure and temperature, they have direct correlation between macroscopic parameters and molecular properties of the gas, in particular some momentum of or some average velocity, like speed of randomly moving molecules, particles which form the gas in the container. Okay, so I will switch the camera. And in order to proceed with this development of molecular model of an ideal gas, or so-called kinetic theory of gases, we need to set certain parameters which define the system. So we need to follow during our derivations, we will follow these parameters which we set at the beginning. So first one, we have total number of molecules is large. So that is important, and actually each of these statements we will mention it during the derivation, so you will see how it affects on the final result. But we assume that n is large, and like comparable to in the order of magnitude of Avogadro's number, which is like in the order of 10 to 23. So it's quite big number. Then second condition we need to take into account is that we have some random motion, and also this motion like of molecules. Let's consider molecules which form this gas. And also, in addition, they follow Newton's laws of motions. So they satisfy this condition. Then third point we need to keep in mind, molecules of this ideal gas interact with each other only where collisions. So there is no any mechanism of interaction. So collisions. Then fourth point, these collisions between molecules and between molecules and walls of the container where gas is confined, they are elastic. So we have elastic collisions. And one more point, that all molecules which form the gas are identical. So all molecules are the same. So we have pure substance without any additional components, just only the same molecules. Okay, so based on these statements, we can start developing kinetic theory of gases. So first of all, what we need to do, we need to consider some container of the cubic container of where gas is located. So let's say we have three system of coordinates, like system of coordinates with three axes, x, z, y, for instance, we can choose. And we have some cube here. Let us try to draw it. Cube. So the side of this cube is d, so it's the same, it's a cube. And we have molecules flying randomly in all directions in this cube. For instance, we have some molecule with a mass m0. It has some velocity vector. And if we can consider projections of this velocity vector on different axes. For instance, this x component of this velocity will be v xi. So vx is x component of velocity, and I is just statement that it's some molecule from large number n, capital N, some ice molecule. Okay, so in this container, we have maybe define these conditions here. So in this container, we have n molecules, and they create pressure on walls, which is P. So, and volume of the container is V, which is equal to dQ. And D is the side of the cube which we consider. Okay, now we consider not all molecules, but start from one. And since we want to, at this point, find the relationship between pressure as one of state macroscopic parameter and some microscopic quantities, like some molecular properties. So let us consider one molecule which interacts with the wall of the container. So here we have wall of the container. Here we have some molecule with mass m0. This is velocity vector of this molecule. We can put it VI, so also here I. Then we have two components. We have, let's say we have two axes. This is X, this is Y. So we have one X component and Y component. So this is the initial condition. Then we have Vxi and Vyi. Then it at least commits some collision, elastic collision with the wall. We have mirror reflection. Here is our molecule after collision. It has the same in magnitude, but different in direction. Velocity vector, Vi. And also we have two components. So we have, in this case, it will be minus Vxi, and this is Vyi. So we see now what we want to consider, the component of, like X component of velocity, because that is what will have some impact on the wall. And actually, we will come to this point when we can transform this effect on the wall and present it in the form of pressure. So we consider the change. So in the X direction, momentum, initial momentum of the molecule, let's call it P. It will be confusing, so probably just P1 will be m naught Vxi, and the momentum after collision, P2, will be minus m naught Vxi. So now we need to find the change of the momentum of this molecule after elastic collision with the wall of the container. So change delta P xi of this particular molecule will be equal to P2 minus P1. So difference between final and initial momentum, minus m0 Vxi minus m 0 Vxi. So which is equal to minus 2 m0 Vxi. Okay, so we got the change in momentum because of collision with the wall. And now we can write this impulse momentum equation. So we have some average force, Fxi, which is force exerted on the molecule from the side of the wall, times delta T collision, let's call it. It is equal to the change of momentum that we remember from the course of mechanics. And this will be equal to minus 2 m naught Vxi. So this time of collision is kind of a tricky time because very short, it's not easy to define. However, we don't need to do this because what we can do, we can consider a longer time. So we know that if our molecule just hit this wall, there is some minimum distance along axis x, which this molecule has to travel in order to hit this particular wall again. So if you look here on this figure, it means if it hits the wall here, it has to travel to the opposite wall and then come back in order to hit this side of the container again. So means that it should travel distance which is equal to 2 times d. And we know that it travels with this Vxi speed along the axis x. So that's why delta t between two adjacent collisions with the same wall of the container will be equal to d divided by Vxi. Okay, now we can use this time for impulse momentum equation and just write that we will have some F average I. I don't put X just to have some option to distinguish between them because it will be different for average force times delta T equal to minus 2 m naught Vxi. So now we have kind of well-defined time interval. And what is important, we need to mention that since we know that during this time interval, this particular molecule will hit this particular side of the chamber of the container only once, we can extrapolate this averaging for a long term, like which for some long time, which consists of many time intervals delta t, because that will not change the average force. So you will have only one collision per delta t. So if you add up more collisions and more intervals of delta t, average will be the same as for one interval delta t. So that's why it can be extended for a longer term in terms of time frame. Okay, now let us maybe determine this average force, which up to now we consider this average force which is exerted on the molecule from the side of the wall. So this is Fi. Sorry, it's not vector, it's just average. Is equal to minus 2m naught Vxi divided by delta t. So we know that delta t is defined by this equation, so we can use it. And we get the following. So it will be minus 2m naught Vxi divided by 2d and times Vxi. So 2 and 2 we cancel out. We get minus m naught Vxi squared divided by d. Okay, so this is our average force. And let it write on the second slide and continue. So this average force on this particular molecule exerted from the side of the wall will be equal to minus m naught Vxi squared divided by d. So now we need to apply third law of motion, like Newton's law, and that is the fact which we mentioned in these initial statements, that all these collisions, they follow Newton's law. So we can apply this Newton's law for this particular case and consider which force will be exerted from the side of the molecule on the wall, because we want to calculate pressure, and that will be some force per area which is exerted from the side of the gas on the wall. So based on the third law of motion, we can write that some average force, let's call it here wall, will be minus Fi average, will be m0 Vxi squared divided by d. Okay, so this is done. Now we need to take into account the effect of many molecules, because we have many of them which form the gas. So in order to do that, we need to sum up contribution of each molecule. So in this case, we have some average force equal to the sum from I equal to 1 to capital N, which is total number of molecules, m naught Vxi squared divided by d. Since, as mentioned in our statements at the beginning, all molecules are identical, so this m mass of molecules doesn't change from going from one molecule to another. D is just the side of the cube container which we consider, so we can take it out from the factor it out from the sum. It will be m naught divided by d times sum I equal 1 and Vxi squared. So now we apply another thing from another point from the initial statement, which means that this, which tells us that N, capital N, is a large number. So we have many molecules. Since we have many molecules, this average force will be kind of smooth, because we will have very many collisions per second, and average force will be actually equal to the actual force which acts from the side of the gas on the wall. And so it will be kind of constant force. That's why we can go from average to just force, F. So this comes from the fact that we have very many. If we have just few molecules, then there would be kind of spikes of force because there will be little number of collisions per second. However, with 10 to 23 order of magnitude molecules, it will be just smooth, and these spikes will be smooth, and we will get just some actual force, which is constant. So now we need to deal further with this sum. It's not clear. So if we know, we can determine mass of molecules, we know distance, but this sum of x component velocities in second square, it's kind of not clear parameter. So let's see how we can deal with this. So first of all, let us consider some average value. So average value Vx square average. So here I don't put I because it's average for all molecules, not for specifically one. So by definition, average is the sum of parameters divided by number of these parameters. So it will be sum I equals 1 from 1 to n Vxi square divided by n, total number of molecules. And from here, we can write that this sum, which is kind of a tricky parameter, and we want to deal with something else, Vxi square, will be equal to n times Vx square average. So that is already better. We have just some average x component speed in second power. With this, we can substitute this sum from previous equation with this new definition of this sum. So we will get force. Now I don't write average because we remember that it will be actually the constant force. M0 divided by d times n Vx square average. And keep in mind that it's Vx square average, not V average square. This is important. So now we again, it's better than the sum of each x components, but we still don't know how to get this Vx. So for a single molecule in three-dimensional system of coordinates, we can write that Vi square is equal to Vxi square plus Vx, sorry, not x, Vy square plus I plus V that, like z square, and here I. So we kind of split the components of velocity vector of a single molecule into three components. And the same approach can be applied to average velocities. So this is written for a single molecule, but this also will be true for the average values of these squares. So it will be V square average for all molecules equal to Vx square average plus Vy square average plus Vz square average. Okay, now coming back again to these initial statements, we were claiming that all molecules are moving randomly. If they are moving randomly, there is equal possibility that they move in any of these directions, which means that these parameters are equal to each other. So in this case, if they are equal to each other, we can write that the sum is equal to 3 times Vx square average. And now we can calculate Vx square average as V square average divided by 3. This is very important because we can substitute Vx square in our equation here with V square average, like with average of square of velocity of molecules. And that is more general parameter because we don't need to know specifically how this parameter is projected on some axis. So in this case, we can rewrite again our equation will be force equal 1/3 times n times, sorry, need to put m0 times V square average and divide by d. So this is
Excuse me, Professor, we can hear you.
sorry, yeah, do you hear me now?
Yes.
Okay, good. Yeah, something happened with this Zoom. Okay, so I repeat. So now we have force, and we know that pressure is the ratio between force and area. So in this case, it will be force divided by d squared. It will be area of the specific side of the container. It will be 1 divided by 3. And total number of molecules times m naught V square average divided by d cube. And this is equal to 1/3 n divided by v, is d cube is equal to the volume, the total volume of the container, m naught v square average. So this equation is convenient to restructure a bit, and in particular multiply and divide by 2. So we have 2/3 of n divided by v times m naught v square divided by 2. So we see that pressure, which is macroscopic state parameter, is proportional to the directly proportional to the total number of molecules, reversely proportional to the volume of the container, and here, like this, is nothing else as kinetic energy, some average kinetic energy of each single molecule. And that's why we have a direct relationship between kinetic energy of a single molecule and a macroscopic parameter, which is pressure. So this is done. Now we want to figure out another relationship. We need to find how temperature depends on what is the relationship between temperature as macroscopic state parameter with molecular quantities, some molecular parameters. So for this purpose, let us rewrite again last equation, and we can write now, so we just move this volume from the denominator of the right side to denominator of the left side. So we have product of pressure and volume is equal to 2/3 and 1/2 of m0 v square average. So now we need to compare this equation, which we got from the molecular, like from the kinetic theory of ideal gas, with the state equation of the state equation of the ideal gas, which was obtained experimentally. We were talking about this before. So the state equation of ideal gas is PV equal to NKB times T. So KB is Boltzmann constant. So we have the same left sides of this equation, so we can equate the right sides of the equation. And we get the following: 2/3 times n m0 v square average divided by 2 equals to n kb times t. So from here we see that n and n we can cancel out, and also these two cancel out, and we see that temperature is we can express temperature from this equation is equal to, or maybe we'll leave this 2, don't touch this, because we still want to see the relationship between kinetic energy and temperature. So we have 2 divided by 3 divided by Boltzmann constant times kinetic energy, not V square average. So we see that temperature directly defines the kinetic energy of molecules in gas. And this is kind of very important definition of temperature because it tells us that it defines it's a measure of internal energy of the system. So if we have single atomic, like monoatomic ideal gas, then we can write that kinetic energy, so this all was derived for monoatomic ideal gas, and we can write such based on this equation or this ratio. We can write that kinetic energy and not V square divided by 2 is equal to 3 divided by 2 times Boltzmann constant times temperature. So since as we have shown before, Vx average square is equal to V square average divided by 3, we can write that 1 over 2 m naught Vx square, which means kinetic energy, like x is component of kinetic energy of average kinetic energy of molecules, will be equal to 1 over 2 kb times t. And that means that also the same will be true for all other components. So we can write kinetic energy component along axis y m naught v y square average divided by 2 is equal to another 1/2 of kb times t, and the same for x. For z axis divided by 2 equals to 1/2 of kb times t. So we see that since a monoatomic particle which forms the ideal gas under consideration, has 3 degrees of freedom, and degrees of freedom, they represent the number of coordinates, number of parameters which define the position of this particle. For each of the degree of freedom, we get 1/2 kb times t. And that's why total kinetic energy of monoatomic particle of ideal gas will be, as we shown before, 3/2 of kb times t. So we kind of sum up all these components of kinetic energy along axis x, y, and z, and end up with total kinetic energy m naught v square divided by 2, like average kinetic energy of these monoatomic particles of ideal gas, equal to 3 second kb times t. So this is the relationship between average kinetic energy of particles which form ideal gas and temperature. So now let us consider also there will be another useful equation, total kinetic energy of the system with many molecules and capital N. So total kinetic energy is equal to N times 2 this average kinetic energy of each molecule. Then it will be 1/2 of m naught v square average. And this will be equal to 3 second n times of how many molecules we have in the system times kb times t. And as you remember from our previous discussions, we can express this number of molecules in the system via number of moles. And then we can write that it's equal to 3/2 nu, it's number of moles, times universal gases constant times temperature. So if we have a monoatomic case for particles which form the ideal gas, this will be equal to internal energy of the ideal gas. So we have direct relationship with temperature with quite simple equation. So the thing is that if there are not monoatomic structures, but some molecules with many atoms, then additional degrees of freedom should be taken into account, in particular rotational kinetic energy and vibrational kinetic energy, in addition to translational kinetic energy, which is considered in this case. So then the total internal energy for not monoatomic systems will be definitely like more complicated. So we will, I hope we will have enough time, and we will talk about these additional degrees of freedom a bit more in details later. So now one more parameter to define before we finish today's discussion. This is kind of important parameter in kinetic theory of ideal gases, which is square root of v square average, and it's called root mean square. RMS speed. So this is some parameter which is defined by temperature and can be considered as some like average velocity, like speed of molecules of ideal gas. So VRMS is equal to, as we already gave definition, square root of V square average equal to, from these two equations, we can like with this left side, we can write that it's 3kb times T divided by M0, or if we want to express it via the universal gases constant, it will be square root 3 RT divided by M molecular weight. So this is also important equation which you should keep in mind, because very often in this problems for based on kinetic theory of gases, it's necessary to calculate this root mean square, and you can do it by knowing the molecular weight and temperature of the gas which you deal with. So R is a constant, so we know its value. Okay, so this is pretty much everything what I wanted to discuss with you for the relationship between macroscopic parameters, pressure and temperature, with microscopic quantities, which are molecular properties, mass of molecule, m naught, or also speed of molecule, some v square average parameter. So we managed to find these relationships between macroscopic and microscopic properties of ideal gas. Do you have any questions now?
Excuse me, Professor.
Sure.
So the last equation for total kinetic energy, you said that this kinetic energy is equal to internal energy, and do we consider that that the case how we obtained this equation is isolated system?
You mean that we it's not so important to specify that's isolated system or not, because it's kind of instantaneous set of parameters which we have in given time. So in given instantaneous moment of time, we have internal energy of the system, which is defined by this equation which we derive, and then based on first law of thermodynamics, like internal energy is equal to heat times work based on what is going on this system. Either it gains some energy via heat transfer from boundaries, or environment performs some work on the system. This internal energy will change, and thus will change temperature. So in some other moment of time, which will be in some time interval from given condition, these parameters will change, and this equation will still be valid, because we change internal energy, and it will follow this equation in terms of dependence on temperature of the gas. So it should not be isolated.
Okay, and can I ask one follow-up question according to the equation of energies? So if it's not isolated system, do we consider that the work is done by motion of particles? Because we always assume that the volume of this cube doesn't change.
Yeah, so here we consider that volume is not changed, but since particles, collisions of particles with the wall forms this pressure P, which we calculated, then sure, if the volume under this pressure will start to increase, it means that, yeah, this pressure, internal pressure of the system will perform some work on external environment, and that will cause to reduction of average kinetic energy of the system, because this work which is done by the system will cause reduction in the internal energy, and reduction in internal energy will cause, so according to first law of thermodynamics, work done by the gas will reduce internal energy, and according to this kinetic theory of ideal gas, reduction in internal energy will cause reduction of temperature. Means that on microscopical level, we will reduce average kinetic energy of molecules. So this kinetic energy of molecules will be transformed in work done by the system, by the ideal gas.
Okay, thank you.
Yeah, and in the contrary, if work is done on the system, then we will increase internal energy and temperature will rise, and average molecular kinetic energy will increase. Okay. Good. Thank you very much for attention. Have a good evening and see you next time. We will continue to work with this results and concepts of kinetic theory of ideal gases. And later we will finally come up to this second law of thermodynamics, and like introduce entropy, and probably it will be next week already. So we'll be finishing the thermodynamics and molecular physics part of our course, I believe next week. But we still have some chapters to discuss. Okay, have a good evening. Bye.
Thank you very much. Goodbye.
Mm-hmm.